Hello ladies and gentlemen, today we are going to take a look at a couple algebraic methods that we're going to use for solving systems of equations. Our learning goals today are that you can solve a system of equations using the substitution method and also the elimination method. What we've been working on is understanding that systems, their solutions are really that point of intersection or that solution that they share in common, a point that works in both equations. And we saw that graphically by where those lines cross. But sometimes those intersection points are not at nice integer values, if you will, that they're not at nice coordinates. And when that happens, we have to have another method, an algebraic method, one that doesn't require a graph, that would allow us to find those intersection points. So how do we find a solution to systems of equations? Well, we can use the first method, which is graphing, but we just saw that that has limitations. We should maybe use a second method, which is substitution method, and we're going to look at that in just a second. Or we can use the third method, which is the linear combination or the elimination method. And we're going to talk about both method 2 and 3 in this video. So right now, though, let's focus just on method 2, the substitution method. So be thinking about what does it mean to substitute. That's when Mrs. Kincaid is not there and there is a teacher there instead of me. They follow my daily schedule, they report to all my classes in the same way. So they've replaced me essentially for the day. We need to do the similar thing with our equations. So method 2 says we are going to substitute or to replace. We're going to substitute one equation into the other essentially. We're going to substitute an expression from an equation especially into another. So it says example 1, solve by substitution, and you'd want to get this example in your notes. Our first equation there says we know y is equal to 7 minus 2x. The second equation says we have 3x plus 3y and it has to equal 9. Now to do the substitution method, you want to make sure that one variable is alone, and in this case we started that way. This says y, the y that we're looking for, is equal to 7 minus 2x. So that means this 7 minus 2x right here can replace the y because it says y is equal to that. So that means in the second equation down here, where the y is, I can replace it with 7 minus 2x. So it looks like 3x, the plus sign, the 3, but instead of the y, I replace him with 7 minus 2x from the first equation, and it still equals 9. And then we're going to go ahead and distribute. To solve here, we have 3x plus 21 minus 6x equals 9. We'll combine like terms. 3x and negative 6x is negative 3x plus 21 equals 9. Negative 3x, 9 minus 21 is negative 12, and x would be 4. So far we know the x part of my point, you guys, is 4. But that doesn't mean we're done. Remember, we're looking for a point of intersection, so we still need to know the y as well. But we're going to take that x value and plug it back up into one of these equations. Usually it's the top one there that's already solved for y. And we're going to replace that x value now in there. So it says y equals 7 minus 2, and now we know the x is a 4. So we'll have 7 minus 8. So we have y equals negative 1. So I know my y value for my intersection point is negative 1. So that's how you do the substitution method. Let's look at one more. This one also says solve by substitution. The only thing that's different here is I don't have an equation right off the bat that says y equals this stuff. But you know what? I can take this first equation here because the y doesn't have a coefficient that's real crazy like a 3 or a 5 or anything. It's a negative 1. That's fine. We can solve for this y up here, right here. If we get that y alone, we'll end up with something like y equals this stuff, and we can plug it into the other one. So we're going to just take this first equation right here, and I'm going to get the y by itself. So I'm first going to add the x's. Then we'll have negative y equals 4x and a positive 2. Then I'm going to divide by a negative 1. Divide everybody by negative 1. That essentially just changes everybody's signs. So it says, well, y equals negative 4x minus 2. So that means in the next equation, the second one, the one we haven't done anything with, the y here gets replaced by the negative 4x minus 2. So my second equation would look like 7x plus 2, and then I'll replace the y with the equivalent expression, and then go ahead and solve just like we did before. So I'd have 7x minus 8x minus 4 when you distribute equals negative 5. Combining like terms, that's negative 1x minus 4 equals negative 5. Adding the 4, negative 1x equals negative 1. Dividing by negative 1, x would then be positive 1. So now we know the x value of my point is positive 1 comma something. We still need to find the y value. So I'm going to take that x value right up here where it says y equals that stuff again. We're going to plug that x value in now. So it says y equals negative 4 times 1 minus 2. So negative 4 times 1 is still negative 4 minus 2 would be negative 6. So the y value is negative 6. So we found that intersection point without having to rely on graph paper. Now, remember we had said there were 3 methods. Method 1 is graphing, method 2 is the substitution method, which I just showed you. And no surprise here, you guys, substitution method is not my favorite algebraic method, okay? It takes a little bit more algebraic manipulation and a lot more steps than I really like. So method 3 is my go-to. It's the linear combination or the elimination method. And this one's really super important because we're going to use this in a few days to solve for more variables than just x and y. So let's take a look at just this one now. We're going to do a few examples. The linear combination method, if we take a look just at those words themselves, we're still talking about lines, but we're going to combine them, putting them together through addition with the hopes of taking out or eliminating something. So basically, the whole goal of this method is to add equations together, trying to eliminate one of those variables. So let's take a look at this first example here. It says solve this system. 5x plus y equals 6, negative 5x plus 3y equals negative 22. Now remember with this method, linear combination or elimination, we're going to add our equations together. So we're just going to line them up like, old school addition here. And we're going to go ahead and add our equations together. 5x plus negative 5x would give me how many x's? You should be thinking 0. There are no x's. Right, so don't even write them. They're gone. Let's add the next column. 1y plus 3y's would give you 4y's. And then the next column is negative 22 plus a 6. That's negative 16. And then we'll just divide by 4. And we have y equals negative 4. Look at how much work it took to get our first part of our point. That's not so bad. So y equals negative 4. Now what do we do with that to help us find the x? Well, remember we still have to substitute at some point. But I'm going to go ahead and take this y and plug it back into my favorite equation of the two up here, the top one, and that's only because there are no negatives there. So I'm going to plug that y value into this top equation here so that I can solve for the x. So it would look like 5x plus y value, negative 4, equals 6. So that's really like 5x minus 4 equals 6. I'll go ahead and add the 4. So I'd have 5x equals 10. So x would be 2 if you divide. So these are my two numbers I need. So my coordinate is 2, negative 4. That's the point of intersection for those two lines. See, that's not so bad. Let's take a look at another example. We're going to solve this system now. 3x minus 4y equals negative 5, and negative 1x plus 3y equals negative 5. So we're going to go ahead and add together. Now, wait a minute, guys. If we add our x's, do the x's go away this time? No, they don't cancel out, right? 3 plus a negative 1 won't cancel out. Well, let's check the y's. How about negative 4y and positive 3y? Nope, they don't cancel each other out either. See, there's a problem here. These two equations aren't set up as nicely as the ones we had before. But the good news is we can make changes to these equations to make things eliminate. So let's say I decide to keep this top equation as is. And the bottom equation, I'm deciding maybe I want to eliminate the x's. Now notice this top equation here had a positive 3x. What would I need down here in order to eliminate with a positive 3? I'd need a negative 3. Well, I already have the negative sign, but I need the 3 to happen there. And the way we do that is by multiplying the whole equation by 3. So if I multiply everybody on that bottom equation by 3, every single part, so that I'd get negative 3x, 3 times 3y is 9y's, and 3 times negative 5 is negative 15. So I just multiplied that whole bottom row there by 3 from his original equation, and now when I go to add them, look at what happens. 3x and negative 3x now cancel each other out, and we can go ahead and add our y's together. I'd have 5y equals negative 20 if you add the negative 5 and the negative 15. Divide by 5, y is negative 4. So I know I have a negative 4 for the y value. Well, what about the x? Well, you just take this guy right again, like we were doing before, take that y value and plug it into your favorite equation. So I think I'm going to go to the bottom one here the way he started. It was negative x plus 3 times y, which we now know is negative 4, had to equal negative 5. So I'd have negative x minus 12 equals negative 5, adding 12. So I'd have negative x equals 7. So x would be negative 7. There we go. So I'm going to go ahead and say that my intersection point is negative 7, negative 4. So the elimination method requires us to try to strategically eliminate a variable. You may have to edit one or both of the equations by multiplying by something, but we can do that as long as we multiply the whole equation by that thing that we want. So this should look familiar to you. Like I said, you spent some time doing this in Algebra 1, and I want to thank you again today for taking great notes.